So, questions on past stuff or on the most recent lectures?
Why do you use the weird shape L as the symbol for not?
Oh, I don't know why that's used. But yeah, this is the symbol for negation. I don't know where that comes from. It'd be interesting to look up. But there was an old teletype equipment. Key punches always had that on the keyboard. So it goes back at least to, I'd say, the 60s probably. But I don't know why that's the symbol. Someone should look that up. That could be your SLP. Figure out why that's the symbol now. Other questions? So what was the gist of these latest lectures? Propositional logic and so on. What did we learn from those?
Not all statements are propositions.
Not all statements are propositions? So what is a proposition?
All sentences are propositions.
Is that
Propositions define a specific kind of statement.
okay? What kind of statements?
A declarative statement.
Declarative statement, right? Declarative statement that has a truth value. That's a proposition. And like I said in the lecture, you always want to come back to that. When we start writing proofs, we'll start off, let P be the proposition. If it's raining, I'll go to the moon today. And we'll start writing P and Q and not P. And then at some point, people will start writing things like x plus 1 as a line of their proof. And at that point, I get out my red pen and I put an arrow pointing to that and I say, this is not a proposition. And everything you do after that falls apart, right? So x plus 1 is not a proposition. Now, x plus 1 is bigger than 0. That's a proposition. Or x is equal to y plus 1. That's a proposition, right? But you got to make sure that every line you write of a proof, and we'll get to proofs in a few days, is a proposition. So you want to definitely keep that idea, proposition as a declarative statement, in mind. All right, what else came out of those?
Conditional truth tables are funky.
Conditional truth tables are funky. So why are they funky?
Our truth table for P to Q and Q to P, A is good.
Yeah. Because they look like that. And this makes sense. This says if P is true, Q must be true. Well, in this case, P is true and Q is false, so clearly this statement is incorrect. So that's certainly false. This case, P is true and Q is true. That's exactly what this claims, so that's fine. But these two entries are a little bizarre. And it's this if false then anything. So here is a true statement. That's true. If 1 plus 1 equals 3, then I am the Queen of England. It's an absolutely true statement. And it's true because of this quirky first entry in the truth table. Right? If the hypothesis is false, it doesn't matter what the conclusion's value is. The whole proposition is true. But did that example with x bigger than 5, x bigger than 100 help at all?
Yeah.
That's the one that sort of makes a little bit of more sense to me. And as we work with this and use it more, it starts to feel less quirky. Right? We get a little more insane, and it starts to make sense to us, and that's good. But it makes a lot of things work well. All right, so conditionals are a little strange.
Anything else?
We talked about
have a positive inverse of conditional statements from the fallacy.
Okay. So let's try this. Let P be the proposition x equals 5. Let Q be the proposition x is bigger than 0. Let S be the proposition if P, then Q. So this says if x equals 5, then x is bigger than 0. Is that a true proposition? Absolutely. Okay, so what's the converse of S?
The converse is that if Q, then P.
If Q, then P. So you just reverse the order. And this statement says if x is bigger than 0, then x equals 5. Is that always true? No. It's only true if x happens to equal 5. So this is not equivalent to this because this is always true. The converse is a contingency, sometimes true, sometimes not. What about the inverse? Not P implies not Q. If x is not equal to 5, then x is less than or equal to 0. And that's clearly not true either. X could be 1,000,000, and that's still bigger than 0. So this is not equivalent to the original. The contrapositive of S, what does that look like?
The reverse of the inverse.
Yeah. So not Q implies not P, which would mean if x is less than or equal to 0, then x is not equal to 5. And that's absolutely true. If x is not a positive number, it cannot be equal to 5. So this turns out to be a tautology. And in fact, the contrapositive is always equivalent to the original conditional. But the converse and the inverse may or may not be. All right, anything else?
Covered conjunctions, disjunctions, exclusive or.
So conjunctions, disjunctions, and exclusive or. So conjunctions are basically ands. Disjunctions are ors, and XORs are just XORs. They need a fancy name, but I don't think they have one. And so if P is a proposition and Q is a proposition, this is also a proposition. It says P is true and Q is true. And same with an OR and same with an XOR. And XORs just mean that exactly one of the two has to be true and the other one has to be false. It's either, but not both. So I apologize, the video recording for Friday did not work. So you heard the only version of that, and that was probably the most success I've ever had in talking about Russell's paradox and Hilbert and all that stuff. It just kind of like, to me, it all kind of like tied everything in together. I was really excited to have a recording of it, and the recording is gone, so you got the only copy of it. All right, anything else on the lectures? So I meant to be a week and one class ahead before the quarter started, and I forgot to post most of the stuff for today, so that's why it came up over the weekend. But I have rectified that, hopefully going forward. I changed all my passwords over the summer, got a password manager, so that's challenging sometimes. So for week 2, right, we have the preparation for today. The quiz was up there, and October 29th. Wow, that's weird. Okay.
Yeah, it actually says October 29th.
I did
Okay.
it this morning and it still gave me the full.
Yeah.
Okay, yeah, do it. Don't wait till the 29th.
I only saw it this morning too.
So Wednesday's preparation is basically to watch lecture 6 and then do the quiz and look at the homework. And Fridays will be lectures 7 and 8, 2 quizzes and 2 homeworks to look at. And then I've gone ahead and posted the following Mondays so that you don't have to wait for me to get that over the weekend. So preparation for the following Monday will be 1 lecture, a quiz, and a homework to look at. And next weekend I'll fill in the rest of week 3 and the start of week 4 and so on. I'm going to try to make these lecture videos shorter. I don't know, I talked to somebody else and his lectures are about 5 minutes each. And I'm going to see if I can really pare this down to like the essential points and then have you figure out most of the other stuff in homework questions. But I don't promise anything. So we'll see. All right, so let's do some homework questions. And I'm going to say homework 5A. Let's just go ahead and start from the beginning. For question 1, I want you to convert these into propositional logic, right? And so I want you to write very clearly, let P be the proposition, it is raining, right? Let Q be the proposition, I sleep, and then write that first thing using those variables, and do that for all 3. But I really want you to get in the habit of actually writing out, let P be the proposition, and then naming what the proposition is. And I want you to avoid doing things like P equals blah, 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 okay? Because that's a mathematical assignment statement or a programming statement or something like that. I want to be very formal, at least in the beginning of working with propositional logic. Multiple people in a group, most of these things have multiple parts, so I would like you to take turns with who's holding the marker, right? And who's sort of figuring out the guts of these questions. Make sure that you're sort of splitting that up amongst yourselves so that everybody's getting lots of practice on this. So I will walk around and I'll leave you to mess around with this stuff.
Proposition is say Q is and then we're doing S or Q.
Do you have these written down? Because I'm stealing the screen for a minute.
The proposition is if it's not then never mind.
We're currently storing cooked for 1. So
That's what I'm sure they use. I am not being
if it is raining, then they sleep.
It is raining.
Yeah, so this is part A. Yeah.
Peer pressure doesn't keep
If it's not raining or I'm hungry.
why are you setting that to a proposition? Or is reading?
We're gonna add a non.
Okay.
Why don't you just copy the video section?
All of it.
You just made a copy of
It is not raining.
If it's not raining or I can actually read.
So long as we find this page.
So we have 3 propositions.
Oh, right.
It is not raining. I am not
Is this
raining.
the other side over there?
I go outside.
So.
So no, I
Do
sleep.
not. Or yeah, not E.
Then you sleep.
Yeah, part A is
Oh, is this? Oh, it's still recording.
Arrow.
We have.
Initialize them with the.
You can get rid of.
Then we need
Yeah.
some parentheses.
Yeah, I think you need
Is
parentheses.
that room D? Here?
No, around the whole first statement.
So don't forget to actually write the proposition. If it is raining, then I sleep.
Oh, and then A, B, and C are like that.
So we need to, I go outside.
Combinations of them.
It is raining.
Yeah, so A is the first combination. There you go. So that says if it's raining, then I sleep.
I just read on that to see rather than.
So already propositions. I go outside.
So you may go outside.
Yeah.
So our arrow, not raining,
It's just a rewrite.
not, yeah. Or.
If I go outside, it's not raining. Yeah, it's got to be that.
Right. Yeah, and this is worse than.
This is the C where you have the proposition.
Everything.
That's not clear if you're writing a slash.
So he adds.
Arrow.
That's the end. So you want, yeah.
Yeah, I just thought.
Sorry, I got
That's
distracted.
better. So the general idea is
Or.
that you guys
Oh wait, it's not. Wait, this should be.
Let's contribute one.
Oh wait, this should be.
I can say let me be the proposition, and I can just repeat that.
This should be
Say
a
P.
question.
If you break it down into smaller and smaller.
That statement is question or not ready or.
Right, she said it's there now.
Well, proposition, it has to be declarative.
Hungry or is.
You have
It doesn't declare.
That's our core.
Yeah. Making sure the proposition, he is just the person and more.
That's a proposition.
Those are questions.
Oh, they're examples of not propositions. So you should be like, what's the world population?
X plus Y.
So we're over.
Do you want to explain that?
No, you got it right. Sorry.
I am.
Yeah, I don't know why. It's a B.
Yep, yes.
So what is the world population earlier proposition? That's the question.
Exactly, we're trying to find out about
Yeah, I know.
But that's just a question.
I think we're going to take it
So it has to be like. Yeah.
To be able to put parentheses or not be.
We don't have what in front of the proposition. It's not. What in front of the
Yeah, that.
Perfect. 1 plus 1 would be. Oh, I see.
Well, what is it? You're not saying,
How are you?
you're not declaring it.
Yeah, those would be.
Sorry?
Those would be also.
I mean, any.
Oh, I think you're right.
So you're gonna take his 3 word word. You already have one. Anything that doesn't have one specific value.
Can we get different proofs so we can write
Oh, I.
Perceive.
It could be just the word hello. It could be any.
Okay.
Thank you for the introduction.
So, A, but it doesn't matter. We have to write them in order given the following. If the earth is flat, if basketball is fun, or I am fun, there's no ending.
Is there a difference?
That's an and.
Take that.
So if the earth is flat,
That's the term.
and basketball is
Or
fun,
to view from
there's no error.
And then you have to beat
Then what?
What's times 3 and it's not. So it's a basketball.
Earth is flat, and basketball is fun, and then, okay.
or
Okay.
basketball.
So we require like another variable.
But if you're doing English, you can just be
You're not in this true statement. It's not, isn't it? Oh yeah, that is.
two hands.
If the earth is flat and basketball is fun.
Well, I mean, as long as your opinion on basketball is not fun. Otherwise, it's unless you're right.
It's a true false depending on who you ask, right?
Yeah, I'd say that was a
But it's
proposition.
just.
Okay, so opinions are probably.
Yeah, it's a statement, right? Don't know about the truth value.
Okay.
And 9 not. Then you can do like x plus, but that's the community.
Yeah, just no equals.
But wait, if you can notice that, you're going to turn it into.
Or basketball.
Two things and together, then it turns into
Just, I don't think you have to watch it. Just start with A.
Oh, yeah.
Maybe right. If I go with Earth is flat.
The earth is not flat.
Basketball is flat. And
Basketball is not
Basketball is not fun,
Yeah.
and I am not.
it doesn't work.
Yeah.
If the earth is flat, basketball is fun.
So it's gonna be
Basketball is not fun, or I'm not.
I wouldn't normally ask you to simplify these though. Normally you just write them exactly as they are, but it's interesting to write down other versions of them and convince yourself
But
why they're
there's
the
no-
same.
I know, it's just like it's incomplete as it is. So I think if you just add like the then,
I thought that was the goal of that one.
Oh yeah, okay, that's right, that's why with C and D there. They say the same thing
Or
differently.
not say.
Yeah, that's right.
What is the difference between those two? Okay. It's the same thing as C. Or.
So I think I write that basketball isn't fun and I'm not.
Should it be just not fun?
I'm left-handed instead of right.
Oh, I was thinking C.
Yeah.
Well, it's a C ball.
Oh no, we got the earth is flat.
Basketball is not fun.
And then it turns out when you just said there, actually.
Can we erase this? You good?
You're good.
Right.
Inverse the other. Right.
No, it's just.
I have the time, but I don't have the time, I don't care to. I'm not hungry anymore.
So it's saying the negation of A and C.
Well, the thing is with this one, you're just doing if basketball isn't fun.
Well, it can, but
You're
if
basically
you,
putting it in parentheses.
the
Like
goal here is to write it the way it's written there.
Like, you gotta like declare it and then.
So it's negation versus
Basketball is
This is really hard to read.
So it'd be like 90% basketball is fun, and I'm the queen of England, how many?
This is more like.
Yeah, basically.
where they just ask you that same question.
Okay, so I think there's a better way to phrase these
Exactly, and it's
something like that.
So basically, you do basketball is fun, and basketball is fun. So it's basically like stupid grammar thing where like someone will say something and they just sarcastic kind of ignore. Basketball. That's not even English. That's what it's called. Basketball is fun.
Basketball
Does that make sense?
The following is not fun. Basketball and I'm the queen of it. So the following is not
This is funny.
basketball.
No, see, basketball is
So
queen of
it's
England.
This is basketball.
Yeah, that technically works.
So I was thinking
Not use that in a conversation.
It's like slang.
Yeah.
Early on.
So is this C?
Yeah, we
So untitled Disneyland or I'm going to China. That you say it was a word statement.
I'm not going to Disneyland. Basketball
Because
is
well, then the right translation English word or Phoenix.
You don't need.
What it really means is
Should table really is.
Yeah, it says or through that.
But they could help you.
the truth table for an or is false true true.
Left or right, but not right. Then can you change the actual proposition itself? Or do you have to keep the proposition the same and add on to that to make it when we write propositions, do we have to keep this exactly the same and then add on to that? Or do we change
We're just
that?
like loosely fitting it to make a sentence. That it conveys something.
That's real.
If we use or,
Yeah,
So
so I think that means anything that actually chooses between two things.
But you can't see.
So like, do you want one or two? You can't answer none and you can't answer both.
Yeah.
Either left or right.
Oh, you.
and then here's a.
I just said it.
Well, you have, as an example, when someone's sending us from a user,
Do you want one or two?
there's just a statement.
Why not?
This doesn't match this, or this matches that.
Or cracker.
That is
Well, no, they can have to say both.
They only get one though.
That's Iris. That's the rule.
Just write it as
No, just for not.
I choose to save my vote.
So what does B say?
You don't get to live in this universe.
No, don't put the negative on.
So what does this thing inside parentheses say?
That's just part of what that
Basketball is
How about go undergo reclamation
Oh, yeah.
if you choose not
Put a
to
knot around that whole thing.
So
And
we
then change B, or false true. B and C is basketball is fun and I'm.
Well, there's always another option.
Yes.
What do you mean always
Like,
like
it's not true. I'll always choose
not to answer the
basketball is fun and I'm.
You can choose neither. I guess there's a valid X or you can choose neither. You just can't choose both.
No, in
So
Zord,
you have to choose
Saying,
one.
in
but
Zord,
something like that is not true that basketball is fun. This is more.
because again,
If you're
different
strictly
principles
transcribing
work.
like here,
Okay.
this is
So like,
left
change,
or right.
You're thinking of the second conditional statement.
Okay, so that's
They're being pushed forward by a piston. And if you're
you can, but you're not supposed to for that.
So left would be straight or right?
But you can do something.
Yeah, so
Oh, okay, okay.
that'd be the negative, and the negative, that's how we work.
Yes, true. Well, P is opposite of Q is opposite. So, from or true. Or it could be both. Time when both of them are.
No,
Not this. So anytime that this is 0, this is a 1.
Yeah.
And then not P or not Q. So
I mean, you
P
could
or
just
Q
put
is
it
0.
here.
And that those two matter.
Yeah.
Because this is off. Yes. If you want these loops, they will only work each
You can't physically go both straight and to the right. And you do either go be
Oh my God, it is.
right, it's truth table, not P
So,
or Q.
is that the end of your proof?
Yes.
So what's the Morgan's theorem say?
The opposite one also.
We should really do
The
the
other side of it. Or it'd be from
Morgan's
not
theorem
P or
was
Q instead of not P and not Q.
So, no, you only do one direction, but can you write down below that what Morgan's theorem actually states?
So you're gonna have to do true, false. So you're at,
The mouthpiece, everything. No way to
These are.
P or Q. So P or Q, Q would be
Okay.
false.
So you found the truth table and the truth for not
P or
theory, not
Q would
theory,
be true, so false.
Yeah, no, but it's cool. All right. Good for now. So that up on the board, make some comments. You want to go on? So 16.
And then
All right,
you're
not being where that.
not P or
Find a truth table.
Boom.
Q, it's a completely different question. P not.
This is our
Okay.
Yeah, or 6, I guess.
Yeah, good. Alright, leave those on the board. We're good to go.
Leave them on the board?
Yeah, leave them on there. We're going to talk about all these.
Okay, so we should move on to.
You can go on to the other ones, but leave those intact. I really like your answer for 4. It's a good illustration.
Here, P not is true.
Alright, what is this? An example.
Neither P not or so or not.
Homework or
Oh, yeah, this would be P not would be 0, Q would be 1.
Okay, so.
Q is 1 or.
At the ready.
Yeah.
Not P or Q. True.
So this is same Q as writing in English what
The rest
is
are false. Not P. True. And something and.
Yeah.
Yeah,
The key opposition be
all for us are false.
A or B not is equal to A not and B.
false and false. False.
Okay.
Cool, that's good.
This theorem has 2.
Add on this one. So that's
Yes, 2.
P or.
You don't have to prove them both, you can just prove that one.
Okay.
That's good.
I only have one cat.
The entire thing of 9.
Yeah, but if you're going to do it with this is plus.
Okay. Do we have the next problem? You're carrying the team.
I'm just carrying weight in the back.
Is equal to P naught.
And then that didn't work out. Right example of a conditional statement by applying proposition P and then writing English that says P.
Right.
Okay, where was the truth?
Really like
I'm hungry. Then
So let's go ahead and talk about these for a minute, and then go on to the next problem set. So first two statements, pretty straightforward, right? First two questions. Third question, basketball and flat earth. So the thing I wanted you to note here was that on question C, right, you're writing a statement and it sounds kind of quirky. It's a false statement that basketball is fun and I'm the Queen of England, right? Question D, you write a totally different sounding statement, basketball is not fun or I'm the Queen of England. Can you convince yourself that those two statements are the same?
yeah.
Right? This is De Morgan's theorem. To say that basketball is not fun or I'm not the Queen of England means it's false to say that both of those things are true. That basketball is fun and I'm the Queen of England. If that's a false statement, it must be that at least one of those statements is false. So basketball is not fun or I'm not the Queen of England. Right? So they're equivalent. They have the same truth value in all cases. So that's an illustration of De Morgan's theorem. Question 4. So English is imprecise. English we use or and sometimes we mean XOR. For example, what time do you want to eat? 6 or 7? You don't want to eat at both 6 and then eat again at 7, right? Well, maybe you do. But we usually mean 6 or 7, but not both, right? So there's imprecision in English, and usually the first thing we do in a propositional logic question is we try to translate from the imprecise version of English that we speak to the very precise language of propositional calculus. And that's why we're writing down these propositions and then just working with these symbols and this well understood nomenclature. And you got Morgan's theorem, good. All right, so question 5, write a truth table for not P or Q, and does that truth table look familiar?
1 and 0.
That looks like the truth table for
That we talked about.
special conditional thing.
Yeah, that's the truth table for if-then. Right? So if P then Q, we can always rewrite as not P or Q. And that's useful sometimes because the conditionals seem more complicated. Ands and ors seem simpler somehow. All right, and then question 6 was a proof of De Morgan's theorem using the truth table. And this is not just a demonstration. It's a proof because we covered all possible situations. If you just pick, if you just say P is true and Q is false, and you show that De Morgan's theorem holds, you've shown it for one case. Okay, that's a demonstration. But in a truth table, you're showing it for all possible cases. And whatever P and Q are, you know that exactly one of 4 things is true. Either P and Q are both false, both true, true, false, or false, true. And if you demonstrate that in each case De Morgan's theorem holds, that's a solid proof. All right, so good work on that. Go ahead and take a look at problem set 5B. And these are probably fine to go ahead and do all 4 of them. They're fairly straightforward. And I think we can finish that easily by 2.
Okay.
If I learn then I'm eating.
I just you jumped in and started doing that.
Technically, sure.
So first define and do.
How much is QP? Everyone should
You don't consider that without.
That's fine.
So
Say I'm in this class.
thing.
Yeah.
No, this was the sentence. Then you add part of that. Yeah, like I wrote it and I was like, I got it.
I mean, that's a true thing. It's pretty rarely.
I'm hungry right now. I don't know.
So we have to look at inverse.
I wouldn't eat
Pulled
yet
out
today.
that right when we were finished.
That's on the best. Number 2, using your book proposition to distinguish the converse, inverse, and contrapposition.
Inverse is not
Okay.
P, not Q.
Q.
Is cat are not.
Write in English the converse, inverse,
I'm eating the
Everyone does not need one.
just the inverse.
Not everyone versus everyone does not.
I'm not hungry.
Everyone does not need.
At the end of the day, you should be saying that
Yeah.
not everybody.
the converse is
Okay.
Is it the same or am I?
Says not everyone means that
If
everyone
I'm not
does.
eating, then I'm
Okay.
not.
And here is the difference.
Well, they can write whatever.
With them.
I mean, because it's simply not clear, so it should be.
Not everyone. Okay.
No?
It's
You don't always have to put not.
Exception or best, they're not everyone.
It depends on what you want.
not
But
here.
either way, both should be right.
It's not.
All the arrows are not.
Imprecision.
Between the not Q and not Q.
Yeah.
Be back in a minute. Let's see if I can find a fan.
Yeah, grammar doesn't really matter.
Yeah, we could write the contrapod, but it's logically equivalent. So
So, you want me to read it?
now find the propositions.
Because I'm gonna get hung up on me.
It's weird, okay?
Some propositions being Q for which Q is true, but the converse.
That's simple.
That's not correct.
How am I gonna find out?
Yeah, not everyone needs.
More than
Well, I mean, you could really say these are false. It just
So I
depends
think
on.
like rain and then ground. So right colors ground.
Well, this one's not necessarily looking for a truth table. This one's looking for just like a P and Q, like X greater
If
than
it's
5,
raining and the ground is wet.
greater than 0.
But it could, the ground could also be
But if
wet.
the ground is wet, it doesn't mean that it's raining. And if it's not raining, it doesn't mean that the ground is
Or
wet.
like I go for a run, yeah, only if it's sunny.
Okay,
Not
so I
sunny,
want to
it's not
write
raining.
that out.
So this should be done.
So you can let R
Everyone does not need.
the first define.
I think the full yes.
Like either way, logically makes sense. Well, you can do it with truth table.
Well, this one, it's not looking for a truth table, it's looking for like, that's Q.
Yeah.
Find propositions P and Q for Q low, Q is true, but propositions Q false.
The converse is.
So, this one is almost short because except for this population changes like if X is greater than 0, then X is greater than 5, not
I'll find the
propositions
propositions P and Q for which.
So,
P to Q is true.
you gotta find one that.
Well, if we do X is greater than 5, we should actually edit that statement. If X equals 5, it's Q. I have.
So,
I'm all about the silver.
I think this is.
Now find propositions for P and Q for which.
Well, get the right
Q is
in.
true, but the converse is
And then
different.
you could write like after this true.
That's like
Which is
X,
like a big-
X equals 5.
Yeah.
Doesn't always need to be true. So we find new propositions.
Yes. So let P equal X.
But I think you almost give it.
So
Or
the inverse.
that's like what?
Conversely, if it's unclassified, if it's structured, that's false.
Yeah. Like U, E, opposition, X is greater.
So,
It's not
It's nice to have a
E is greater than 5, then
But
X is greater than
things are
Make it X is greater than So P to Q. P to Q.
Actually, that would not work.
X is greater than 10.
No, well, we have to. It wouldn't be true in the case of this. So the converse is not. Let's say you read it A.
yeah, just to cover it. Yeah, write the truth table for the P.
So find the truth table.
Do you have the definition of double Q?
Because this is now if I live in Washington, oh, we could just write it. It was not after that because it was not them.
Actually goes to no,
Not writing in English, but just doing the truth table. So you can just repeat it, double arrow.
So actually, the
And then nope, so that's it. But the covers and inverse or truth table, Mary take away.
well, this says Q5, I guess. And then Q.
It's raining, then the ground is wet.
That's
Or what does that mean about?
Yeah.
Oh, well, no, it's fine.
Yeah, P to Q and Q to P.
Oh, wait.
I agree.
I think it'd be called close.
So just be talking about sort of
Not wet.
Correct. Doesn't necessarily mean they're false. But in some cases, they're not going to have the same value. For example, if x equals 10, then 2x equals 20. Right? That's a true statement. The converse is going to be true. The inverse is going to be true.
because since P is not here,
Fair enough. More questions?
If I say I live in Washington, I live in the USA, and I don't. The only one that is kind of, the only one that can you a Ferrari title He's really counting down the weeks.
Yes.
It's how much work. That's right.
Yes.
Yes.
Even though it's still falling apart, that's all the water, like, goes into
That's what I understand.
I don't know why, but like when I was doing it, I think it's
If only Q is true, it's both true.
Well, I'm not gonna try to say.
that's where all of them I think there's like 2 degrees that are like a honey pot right now. Yeah, it's something cute.
It's actually exclusive.
I think it's, yeah.
That sounds like it may be because if we were to use this one,
So what we're talking about, like the SOP or the
We got it wrong.
what?
I think it's true, false, false, true.
This false isn't true.
Yeah, well, the SOP is a thank you. Backwards. Take 224, then 222, then 222. It's completely out.
Okay, I see what you're saying. Yeah. True and true. Is it true? Alright, and you're good.
You're saying so
Okay, perfect. Cool. Awesome. So I think everybody's got these. So let's go ahead and sit down and talk about these for a minute, and then we'll move on. So, so part 1 is just writing out a conditional statement. Part 2 is playing with converse, inverse, contrapositive. And depending on what you picked for P and Q, you may already have found that the converse and inverse were false, even though P implies Q is true. And it really depends on what your propositions are. So for example, if we say let P be the proposition, x equals 10, and let Q be the proposition, x plus 1 equals 11, then clearly if P is true, then Q is true. But it also turns out the converse is true. If x plus 1 equals 11, x does equal 10. And the inverse, if x is not equal to 10, then x plus 1 is not equal to 11. That's also true. And the contrapositive is always going to match the original statement. If x plus 1 is not 11, then x is not 10. So in this case, all 4 forms of this conditional turn out to be true. But that's just the way that P and Q were picked. But this is interesting. If P then Q is true, and if Q then P is true. And so that can be written as P implies Q and Q implies P. But we often write that with just a double-headed arrow. I think usually a single one. So P double arrow Q. And that's our if and only if P if and only if Q. So they have to be true or false together. And to write the truth table for that, we can write the truth table for if P then Q. And then we can write the truth table for if Q then P. And you have to flip these around in your head, but basically this fails only when Q is true and P is false. And then we can write the truth table for the conjunction of those. And it's just an AND operation between these two columns. That's your 1, 0, 0, 1, which was what everybody came up with. And you can see here that P and Q have to be both false or both true for this biconditional to be true. And this is called a biconditional. And what's the other name for a function with this truth table?
If and only if.
It's an if and only if. It's also an exclusive NOR. It's a negation of the XOR. It's also sometimes called the equality function because if P and Q are equal to each other, then this function is true. So equality, negation of XORs, if and only if, biconditionals, these are all somehow the same thing, right? Different aspects of the same concept. Okay, well, good. So we're through Unit 6, or 5, A and B. So I know you haven't watched the other videos, but let's see what's in the next homework questions.
I watched the videos.
You watched the videos? Okay.
Yeah.
And someone pointed out that 6A and 6B are not uploaded. They actually are uploaded. I just didn't put them on the playlist. So you can snoop around the channel and find them, but I'll add them to the playlist at about 2:30 today. So let me see. No, I don't want to watch the video here. I want to look at the homework. Okay, so let's look at the identities from the text. I'm going full dark mode here. So, so page 58 of the text has these logical identities, and these should be mostly familiar from Engineering 250. Okay, these are things that we do in Boolean algebra. For example, commutivity. So commutivity talks about changing the order of operands. P or Q is exactly the same as Q or P. And that sort of makes sense in English, right? When we say either proposition has to be true, it really doesn't matter in what order we list these propositions. It could be P or Q, it could be Q or P. And similarly with ANDing, with doing a conjunction. P and Q, Q and P have the same truth values. And the book uses this double two-headed arrow to say basically that this is logically equivalent to this. So it uses this two-headed arrow. Associativity says we can do things in different groupings. If we want to take the OR of P, Q, and R, we can take P and Q, OR those, and then OR the result with R. Or we can take Q and R, OR those together, and then OR the result with P. So we have associativity in both ANDs and ORs. This doesn't always happen in math. There's some math systems where the grouping makes a difference. For example, with matrix algebra, sometimes the grouping of things can affect your answer. Distribution, so if we have ANDs and ORs, where an AND's applied to an OR of two things, we can break that into an OR of two bigger expressions. And it's the same distribution as, you know, A times parentheses B plus C is AB plus AC. Works the same way. The identity laws, if you OR with false, it doesn't change the value of P. right? So it's raining right now, or 1 plus 1 equals 2. It's raining right now, or 1 plus 1 equals 3. The truth value of that statement is the same as the truth value of it's raining, right? Because 1 plus 1 does not equal 3. And when we AND, it's raining outside, and 1 plus 1 equals 2, that's true precisely if it's raining outside is true. So, so you can read these and listen to them in the video. When you AND something with its complement, that's false. It's raining and it's not raining, that's a false statement. It's raining or it's not raining, that's always true. It's raining or it's raining is the same as it's raining, and so on and so forth. It's raining and something that's false is always false. And it's raining or something that's true is always true. And then absorption is really powerful. So this says P ANDed with this disjunction, P or a Q. Q doesn't matter. And this kind of makes sense if you think about it, because suppose Q is false, right? Then P or a Q is just going to be equal to P. And so this whole thing is just P and P, which is P. And if Q is true, then this statement's going to be true, P or Q. And so we have P ANDed with true, and we know that's just the same as P. So sometimes your expressions come into one of these forms, and you can throw away one of your variables. And De Morgan's law, you know, an involution is just double negation, not P is equal to P. So why do we care about these? Because we're going to be doing proofs, and we're taking sentences, and we're translating them into these kinds of expressions, right? Propositional logic. And we're trying to show something. The thing we're trying to show can also be written as one of these expressions. So the question is, can we take this set of expressions that we know are true and somehow prove that this conclusion is also true? And we can do that by applying these different rules. If we have a P and we're ANDing it with something that's false, we can replace that whole thing with false. So you're basically doing algebra, right? In algebra, when you're trying to show that some equation is equal to some other equation, you start doing things equally to both sides, right? Things that don't change the value of your expression. Same thing here. And there's no algorithm you can follow that will guarantee if you follow these steps you're going to get to the conclusion of your proof, right? It's really a trial and error thing. It's getting comfortable with some of these identities and getting comfortable with doing enough problems that eventually when you have a problem on a test or homework or something, it either looks like something you've seen or you've gotten very good at just trying different things. Right? Well, let's throw De Morgan's theorem at this, because we have a negation, we have two things ORed in parentheses. Let's put De Morgan's theorem on it and see if that helps. So it's a trial and error process, but it's a puzzle. Right? If you like doing puzzles, you'll like doing proofs, because it's basically trying to figure out some way to sort of simplify your expressions until they are simple enough that you can actually like prove your conclusion. And then I got lazy and I just punted to problems from the text. So let's look at some of these questions. All right, so exercise 1, we're given a set of propositions, P, Q, and R, and we create different versions of this. That's better. So we create different versions of different propositions from P, Q, and R. P and R ORed with Q, R ANDed with P, not R ORed with P, and so on and so forth. And the question is to figure out which of these expressions are equivalent to each other. So let's just play around with this a little. So P and R ORed with Q. Anything we can do to rewrite this in a different form? Say again? We could, but let's not. Right? We could do all of this by writing truth tables and then finding which truth tables agree. But let's do this by using identities and rewriting these expressions.
You could have P or Q and P R or Q.
R or Q, right. We can use distribution, okay? And technically, if we want to be absolutely precise about this, right, first we would use commutivity and say this is equivalent to this. Right, we switch around the order of these. And once we've switched around the order, now we have this thing distribution, which says if we have something ORed with an AND of two things, right, we can distribute that OR across the two terms. So this would be logically equivalent to Q or P ANDed with Q or R. And that may be one of the expressions in that list for that question, in which case we would know that this and this were equivalent to each other. So suppose we have P and not Q, ORed with Q. So, and I won't usually be really picky and say you've got to put the Q on the left side before you can use distribution. So let's just go ahead and use distribution. So this would be P or Q ANDed with not Q or Q. And we're not thinking about what these things mean, right? We're kind of blindly just picking up symbols and moving them around according to these identities. That's what it means to use these identities. So this says I can take these two things and OR them, and I can take these two things and OR them, and then AND those two expressions. So there's P ORed with Q, there's not Q ORed with Q, and I'm going to AND those together. Yes?
Isn't not Q and Q just one?
It is, but we're not there yet. We're going to do one thing at a time, which you probably did, but you went ahead and did the second thing too. So we're going to do that next. We're going to say not Q or Q. We have an identity which says this is always true. So this is P or Q ANDed with true. And we have another identity we can use now. So what can we do to this?
Anything ANDed with true is just whatever itself is.
Yeah, P ANDed with T is always P. So this is just P or Q. So now we've shown this big expression is logically equivalent to just P or Q. So we may have started with a word question which says, you know, the earth is flat and basketball is not fun, or basketball is fun. And we could translate that to simply the earth is flat or basketball is fun. So it's ways to simplify. All right, so there's a question for doing truth tables. I don't understand 5, that's okay. All right, questions so far? We're actually flying through a lot of the lecture videos, so hopefully when you watch those, there will be a lot of review. Let's talk about rules of inference. And yeah, I think I can start chopping these videos down to make them shorter. So rules of inference are this next table in the book. which is like page 59. And they have fancy names like detachment and disjunctive addition and things like that. But let me give you a real example of a rule of inference. So suppose P and Q are propositions. And suppose we're told if P then Q. We have no idea whether this statement is true or false. Okay, it's a proposition that has a truth value. Could be true, could be false. Here's another proposition, P. Could be true, could be false. We don't know. So let's put some things on these. So let P be the proposition you are a cat. I'm going to go with the cat theme. And let Q be the proposition you like fish. So P arrow Q is a proposition. What does it say?
If you are a cat, then you like fish.
If you are a cat, then you like fish. Is that proposition true or false, or don't we know? I'm not a cat. And even if I was a cat, I'm not all cats. Now, cats seem to enjoy fish, but maybe they hate the smell and they eat it to get rid of the smell. I have no idea. I've never studied cat physiology. I really don't know if this proposition is true or false. What about proposition P? Are you a cat? Maybe. You could be a cat imagining you're a student at Clark. It's possible. Really don't know if P is true or not. So a lot of times there's very little we can say about the truth of these individual statements, these propositions. But here's something we can say absolutely is true. If this proposition is true and this proposition is true, then this proposition is true. If it's true that if you're a cat you like fish, and if it's also true that you are a cat, I can guarantee therefore you like fish. And this is not saying anything about the truth of this statement or the truth of this statement or the truth of this statement. Okay, it's saying something much broader. It's saying if these two things are true, then this conclusion is true. It's a subtle difference, but it's important. And in some sense, this is all we can ever really prove with any of this stuff. We can't actually prove that you're a cat or the earth is flat or basketball is fun. But we can prove that if this is true and this is true, then this must also be true. And so rules of inference are things like identities that we can use to prove propositions based on the truth value of other propositions. And the first rule of inference is exactly this. It's called detachment. And it says if P implies Q is true and if P is true, then Q is true. And the double arrow sort of tells us that we're saying everything on the left of that implies everything on the right. It's just saying if P implies Q and P is true, then Q is true. And when we're doing these proofs, we usually write them in this form where we write the things that we know are true, one below the other, and then we draw a horizontal line, and then we write the conclusion that is either true or that we're trying to prove is true. All right, with me so far? So let's stick with these propositional variables. P is the proposition you're a cat. Q is the proposition you like fish. And if it's true that if you're a cat you like fish, and it's also true that you're a cat, then you like fish. Okay, here's another form of this. Suppose if P then Q is true, and suppose Q is false. We can guarantee that P must be false. So we're still saying if you're a cat, you like fish, and we're also saying you do not like fish. Guarantee you cannot be a cat. Why? Because if you're a cat, you like fish, and you just told me you don't like fish. So this is another valid rule of inference. And this is something called indirect reasoning, or contrapositive or contradiction. Indirect reasoning in the book. So given P and Q and given not Q, we can conclude not P. So those are two rules of inference: detachment and indirect reasoning. All right, there's a flip side to this, because sometimes someone will try to make an argument like this. So if P, then Q, not P, therefore not Q. And this is not valid. So in our example, what is this saying? If you are a cat, then you like fish. You are not a cat, therefore you must not like fish. Doesn't follow from those first two propositions. It's possible you're a person and you like fish. So this is what's called a fallacy. And it's got a particular name. It's the fallacy of denying the hypothesis. And it's a fallacy we see all the time. We see it in the news. We see it in Washington. We see it all around us, right? And it's just an error in logic. Now, it's possible that not Q is true, right? If you're a cat, you like fish. You're not a cat. It might be that you don't like fish. Could be true. But you cannot conclude this from these two statements. Right, so if you murder people, then you're a criminal. You don't murder people, therefore you're not a criminal. Well, not necessarily. You might still be like stealing from people. Okay, and there's another fallacy. If P, then Q, and you try to conclude P. If you are a cat, then you like fish. You like fish, therefore you must be a cat. Doesn't follow. So this is the fallacy of affirming the conclusion. So detachment and indirect reasoning are correct rules of inference. These two fallacies are incorrect. And it's useful to know that those exist and to know what they are. So I'm going to ask you to get ahead a bit on the videos because we're going faster than I thought. So you might want to look ahead a little bit on the videos, but we'll work on these homework questions on Wednesday, and if we finish those in time, then the same thing, we'll talk about the next ones and start working on those questions. Okay, so Friday, class will start late, right? So I have my seminar at 12. I'll remind you on Wednesday. my seminar at 12 in room 151 that goes from 12 to 1, so I won't be in here until 1 o'clock. So it'll be a half hour short. You are invited to come to the seminar at 12. It should be a good one, I'm hoping. I'm excited about it. And that'll be our Friday weirdness for the week, I think, will be the stuff I talk about in there. And there'll be some tie-ins to stuff we do here.